first part.
Just separate each other.
Yeah, it's crazy. You can even look at it as substitution. Right? You know y is x plus 1, so I can substitute it in the other one. Yes. It's another person. We're up to 7. Sorry, buddy. All right. So yeah, so if I put this here. This is where you gotta be a little careful. So subtract 1, sure, that's great. Can you divide by x? You never, ever divide by a variable expression. Because what are you not allowed to divide by? 0. And if it's a variable expression, do you know if it's 0? Could it be 0? Yes. So you never divide by a variable expression, right? So what I have to do is I can subtract x from that side. And then I just, what do? Back. Cool. Take x out. Then I can do this. So we get 0, 1, negative 1. So there's the 3 places that they intersect. I should have put something at the beginning. That's my fault. Because later I show you I'm really only interested in the first quadrant. Just kind of focus on that. So I got 0, 0, and 1, 1. They definitely both go through there. One of them is a straight line. Okay, that kicks a lot of ass. I feel like that's really true. Now, in these kind of problems we're about to get into, all of chapter 6 basically, what really matters is which function is on the top, which function is on the bottom. Right? So let's put in a point. Like, what do I get when I put 1/2 in to execute? What did I just?
I was gonna say, and you should start at 1.
Yeah, it should. I love myself so much. All right, let's try this. I love it. I love it. Okay, so we got this here. Right? So at 0, they're both 1. And at 1, they're both 2. There, we just shift it all up, Jeff. Good job. Okay. So y equals x plus 1. Starts at 1, goes up 1 over 1. Bam. Here, Angel. Sure. All right. So that's nice and straight line. And also, real quick, you can see that when I put a 0.5 in, I of course get 1.5 out, right? Now, when I put a 0.5 in to x cubed plus 1, because I know it's not going to be a straight line, it's going to be curved. You probably should know that it's going to be kind of like concave up, right? Well, let's see. I don't really need to know that, because if I plug a 1/2 in, so if I plug a 1/2 in, what is 1/2 cubed?
116?
No, too many 2's. 1/8.
Oh.
It's going to be 1 and 1/8, right? Which is like 1.125. Right. So then 0.5 for x cubed plus 1 goes to 1.125. Well, here's 1.25, so then halfway there. So that's where my x cubed plus 1 is, because it should go kind of like this if I keep going, right? So I've got this kind of banana-shaped region. There's going to be a lot of banana-shaped regions. Okay. All right, so there's the first thing. So find out where they intersect. And again, it's fantastic. As I get older, nifty things happen with my attention span. When you plot those points, you actually plot what the functions are doing, right? It's probably a good idea. But the nice thing is, when you find the points of intersection, that kind of gives you some anchors, and then you just really have to fill in what the function looks like. So what's part C? What would the integral 0 to 1 x plus 1 dx, what would that represent? What would that tell me physically? Which line does it refer to?
Oh, the area under the line of x plus 1?
Yeah, it would represent the area from 0 to the green line, right? So it would be this big trapezoid, yes? It would be this trapezoid here. But the green line is one side, right? The area of that, correct? What would this integral represent?
The area under x cubed.
The area in here up to the purple line. Or maybe we'll exclude it. Okay. So old news. Those are both old news. So what if my question was, find the area between x plus 1 and x cubed plus 1 in the first quadrant, right? Well, how do you do that? So I call this a cookie cutter problem, because the area with the green line is the big whole thing of cookie dough, right? It's rolled out, and for some reason it just came out looking like a trapezoid. And then I want to cut that banana shape out and just focus on that, right? So what does that lead to? If I cut something out, what am I doing with the rest of the sheet? I'm subtracting it from it, correct? All right, so I'm probably making a big deal out of nothing. If I want to get the area in the banana, probably a phrase you never thought you'd hear. Get the area in the banana. I have to take the area under the green, between the 0 and the line, minus the area between 0 and the curve. Right? Okay, so I kind of gave away parts E. What would this represent? It would represent the area of the banana. Right? Go ahead and do that real quick. And just to help you out a little bit, what do you do first here before you start to do anti-derivatives?
Oh, you separate.
Yeah, you bring the negative in, right? Cancel some stuff out. Why is this one first and this one second?
Because the line is the graph that's on top.
Yes, this is the top function minus the bottom function, because I can't have a banana with negative area. Right? See what I get? What do you get when you integrate this here?
That 1/2 x squared
1/2 x squared,
minus 1/4 x cubed.
1/4 x to the 4 from 0 to 1. I'm going to plug a 1 in, make it a half minus a 4, which is 2 fourths minus 1 fourth, so 1 fourth. Don't give me no decimal shit. Sorry. Technically right.
That was a little intense.
And then when I plug a 0 in,
Zero.
0. Okay, so this is the answer. One good thing about that answer is it's positive, right? So even if I had a problem, has everybody got that? Even if I had a problem that had like one function down here and the other function like that, and I want to find this area, that area will be positive. We're being more specific now. Integrals in general are from the x-axis to the function. So the integral of a function could be negative, because maybe you're losing stuff, correct? But here I'm asking for the physical area between those functions. It must come out positive. Maybe, yes?
So if you got a negative answer, would you just make it positive, or you did something
No,
wrong?
you did something wrong.
Okay.
Most likely, you just had the wrong function first. Which does mean you could just make it positive, but you know, you gotta make it.
Got it.
Don't just make it positive, yeah. Yes?
Is it always the case that like if you take the integral of one and the integral of the other, you subtract that?
Yes.
It's the same thing?
Yeah. And the reason most of the time that we don't do them separately and then subtract the answers is because of what just happened there, something canceled, right? So sometimes you can have a lot of things canceled. So that's why you can sort of jam them together just in case you're like, oh, please, something cancel.
Yeah.
Right? Okay. But in general, you could use both separately, subtract what you get. Yeah. So let's get freaky. It's a weird way to say it, Jeff, but what we're about to do is something that you don't get to do a lot of. I really want you to understand. A coordinate system is very arbitrary. I could do it like this. If I have something sitting on a table and I want to kind of use a coordinate system to describe it, I can put the coordinate system down any way I want to. Does what I'm saying make sense? Maybe. So we had a problem where it was like, find the, we had an ellipse, remember this ellipse, and they had to put a rectangle in there. We decided to make the coordinate system match up, be parallel to the sides, right? And we put the center in the center of the ellipse. Did we have to do that? No. I could have oriented it any way I wanted to, but that was the smartest way to do it. If I would have oriented it a different way, we would have gotten the same answer, but it would have looked a lot worse. Would have been really gross. Now the next stage of that is x-axis, y-axis is arbitrary also, because I could just turn the whole thing. So everything we've done so far in relation to the x-axis can also be done in relation to the y-axis. What the shit am I talking about? Hold on. So the integral f of x dx from a to b is our standard blah blah blah. A, b, there, right? So what does this mean? Yeah. So now it's got to be a function of y. So now it would look something like, so here would be my A, my B. So it would be this here. And if you just do this, it sort of lines up with what we're used to. Which axis is which is arbitrary. Right? We could have called slope run over rise. We could have made everything in terms of y instead of x from the very beginning. X equals my plus b. I might be pushing it a little much, but do you guys understand how it was really just a choice we made? So what good does this do? Well, let me see. Let me give you a specific example. Can we currently do this problem?
Yeah.
What's the integral of natural log? Do we know? I know what the integral of 1 over x is, but do we know what the integral of natural log of x is? If you think about it for a minute, we have no way to do that. We have no way to do it. Could I use that newest thing we learned? U sub. If I let u equal natural log of x, du is 1 over x. Is that in there? No. Am I missing just a constant? No, I'm missing a functional piece, right? 1 over x. It's not there, so I can't do shit. Now, just a teaser. The very first thing you learn in Calc 2 is how to integrate something like this. But anyway, that's too much for us. We currently can't do this. So watch this. So this function is this, right? Can you solve that for x? Can you solve that for x?
Yeah.
Yes. What is it? How do you solve it for x?
So just
What's the base? What's the base of ln?
oh, E.
E. How do logs work? E to the y equals x.
Yeah.
Right? Yes? Now watch this. Okay, go on. This is x and x, correct? How do I know those are x's? How do I know that's a value of x and that's a value of x? How do I know that?
It's in terms of.
Good, dx. I love it. So there are certain things we haven't had to really think about much because we haven't done much yet, to be honest. But now it's really important for us to focus on this because guess what? Could be this sometimes. Oh, shit. So if I'm given this, I know that these are what x are doing. If x is e squared, what's y?
2.
2. I love it. So this would, all right, now watch. I'm going a little bit, I really want to show you some motivation. We're going to get to a point where we're able to do this fully. This one's not that terrible. It's really obvious that this integral sucks. Why? We don't know how to do it, that's why, right? But the inverse of this, how do you feel about integrating something like that? That's like the best function ever. Here's one of the worst functions in Calc 1, because we don't know what the shit the integral is. This is the best function in Calc 1. Hello, right? So if I just take this dumb thing written in terms of x, and instead write it in terms of y, I can find this crazy ass area, right? So help me out. So if I change it to dy, this is e to the y. When x is e squared, y is obviously 2. Are you guys with me? So, and then when x is e to the first, y is 1. And then that's easy to do, right? You do that all day long. That's crazy. Let me stop for a minute. Let me let you soak that in a bit. Okay. So there's huge motivation to be able to understand dx, dy, the difference between the two, because here's a really quick example, right? Okay. So coming back to this, let's do this one together. Dadgummit. Okay. So how do I do that first piece? Yeah, set them equal to each other. Awesome. All right, how do you solve that?
Add the y squared.
Yep, good. Get it equal to 0, right? So add y squared, subtract 6y. Jeff, you can do it, buddy. Yeah, divided 2. And real quick, why am I allowed to do that? Because of course the 0 eats that for lunch, right? So I need quadratic formula? Shit, no, so don't go for it all the time. It's crazy. How do I factor this? So that's y, or y squared. They have to add to be negative, multiply positive, so they both have to be negative. And of course, the only way to factor 5 is 5 and 1. The only way to do whole numbers anyway. And thankfully, that's minus 5 minus 1 is minus 6 y. Right? So what do I get? Y equals 5, y equals 1. Now, let's do something I didn't do on that first problem we did. I want to know where they intersect. So normally when I want to know where they intersect, I find the points of the intersection, yes? So I know one point, where do I put that 5 in that point? It's the y value, right? So it goes here. So these are the parts that are going to be different to us. We're used to the input being x, so we've got to remind ourselves if it's y to put it in the right place. Now if I put 5 in, so either one, it's got to be the same answer, yes? Because that's the whole point. So that's a way to check yourself. If I put a 5 in, I get negative 25 plus 30, looking at the second dude. Right, negative 25 plus 30, so that's 5. If I put the 5 into the first dude, I get 25 minus 30 is negative 5 plus 10 is 5. So they both agree. And again, it's a quick little way to check yourself. Because that point I'm getting should be working in both functions, the whole idea. So what's the other point? Yeah, when y is 1, put a 1 in. Negative 1 plus 6. 5. Let's check this guy. 1 minus 6 is negative 5 plus 10 is 5. Crazy. Alright, so let's see. Do you guys know, by the way, do you know what this is going to look like? Yes! Yes, thank you. Parabola opens this way, right? Positive, going in the positive direction. I love it. Okay, so let's plot a few points. All right, let's see if you can get more specific here. So 5, what is, there it is. 5, 1, 5, 5. Oh, there they are. They're right there. So, and what's the other parabola look like? So one of them is going to be like this, and the other one's going to be the other way, because it's negative, right? So it's going to open up in the negative direction. So it's going to make this thing that sort of looks like it wants to be an ellipse. It's going to be the area between them. So if I do it real quick on the board, that would probably go that way, probably go that way. That's the area between, right? Okay. See if you guys are cool with this. Can you tell me what the y value of the vertex for each of these parabolas is by what I've graphed so far? What's true about a parabola? If I have a point there, there's got to be a point there. So where's the vertex when I have a point across from another point? Isn't it right in the middle?
Yeah.
So I have a parabola that opens like this and like this. There's a point of 5, there's a point of 1. So there's got to be, the vertex is going to be at 3. And of course, the vertex is the most important point, really, for a parabola. So what do I get when I plug y equals 3 in? So we just figured out that the vertex for each is going to have a 3 here. So what do I get when I plug a 3 into the first dude, the positive parabola? I get 1. You gotta be really, right? This is, again, you gotta train your brain. We input in a y, we output an x. And what do I get for this guy? When I put a 3 in. Say again? Yeah, negative 9 plus 18, I get 9. Is that cool? So 1, 3. 1, 3 is one vertex. And the other one is 9, 3. So I've got my, let's call my positive parabola, let's say it's green. So it's going like this. And then my other parabola is purple, and it's going like this. So then the area we're eventually going to want to find is this area here. Okay. So this has happened several times this semester. Your work has been informed by a decent little graph that you sketch, right? And the whole point of pre-calculus is just to put you through it. What do I call pre-calculus? Did I tell you this? Graphing hell, right? So you claw your way through hell, and then you're up here and you're like, calculus, you're no big deal, I can graph shit, right? Is the purpose. So does your graph have to be perfect? Actually, no, it doesn't have to be perfect. I just wanted this one to be kind of really nice. You just need, what is the most important thing to know to find the area between the two? What did I say earlier? Which one's on the top? Now be careful. How do you look at this correctly to see what's on the top? Like that, right? Does that make sense? So which one's on the top?
Negative 1.
The negative one. 11. This one. So it's going to be this guy. Because if I integrated from 1 to 5 of this, wouldn't it just be the area from the y-axis to this? That would be the whole area, right? So what do I want to subtract off? The area from the green line to the y-axis. If I subtract that area off, I'm just left with this in the middle. So it's always, once you get them set up, and by the way, I just gave something huge away. If you were listening, you can answer this question, but I want to know why. What will the integral go from to?
1 to 5.
Yeah, 1 to 5. Because that is where everything's happening, right? From 1 to 5, this finds this thing. Okay, so let's see. Did you do it, Tristan? So if I want to set this up, it'll be integral 1 to 5. How do I know it's that? Because I know it's going to be dy, because I know all my stuff is in terms of y. And I did not give myself enough room. What do I put first? What did we just figure out?
Negative y squared.
The negative piece minus the positive piece, or the up ramp. So let's see what we get. Negative y squared plus 6y. And see, here's a really big mistake people make in general is forgetting you're subtracting the whole thing. So the negative is going to have to go through, right? So negative y squared plus 6y minus 10. Did we see something that looked like this somewhere earlier? Did we see something that looked like this somewhere earlier? Isn't it like the negative of this? And that's basically going to happen most of the time. So again, if I put this like this, if I just turn that, isn't it obvious that I want to go from 1 to 5 because that's where everything's happening? I like it. Now, to be honest, wouldn't I have to reflect this to make it really look more like an x-axis? I mean, do you guys see that? Because it looks like it's going from 5 to 1 anyway. And now it's easy. Of course, like always, the hard part is setting the thing up that I want to attack, right? So it took a while to set this up. Now we can integrate that, no problem. Or, relatively easily. Let's see. What do you get when you integrate that? Good, negative 2/3, y third, which is nice, yeah. The 2 factor just goes back up, so you get 6y squared minus 10y from 1 to 5. It's a big side, so I get 5 cubed is 125 times negative 2 is negative 2/53 plus 6 times 25 is 150 minus 50. That is f of 5, right? Thinking back to f top 2, right? Look at 5a, they get that. So here's another place people make a mistake with the minus. Minus everything I'm about to get, right? And now what do I put in here? What I get when I put a 1 in, correct? So I put a 5 in, got this business. Now when I put a 1 in, so I just get negative 2/3 plus 6 minus, get out of there, y, minus 10. All right, Jeff, master of using space. So let's see. I know some of you guys would have plugged this in on confident by now, but still, you gotta get used to it. I might ask you, give me an exact answer. Which means I don't want to see no decimals, right? Especially with some trig stuff. Oh, baby. So let's see, I get negative 2/53 plus 2/3 is negative 2/48, which is not divisible by 3, it's too bad. So I get negative 2/48 plus 150 minus 50 is 100, minus 6 is 94, plus 10 is 104. I think that's what I did. Okay. It's like 83, 82 and 2/3. It's like 21 and a third, I think. 21.383. I don't know. Yeah? No way. All right. 21. Surprised my brain. 21.3.
It's also 64 thirds. It's also 64 thirds.
Even better. I like it. So remind me, what does that represent? That number?
Between 2 curves.
Yeah, this area that we shaded. I like it. So is that crazy? Is it bad? That is crazy. So it's 2 section 5-3 problems in one. You don't just integrate once, you integrate another function. But what do we do to shortcut that? Like Ricardo said, you could do separate integrals. But to shortcut that, we put them together in one integral so that maybe stuff will cancel, right? We kind of hope. Or maybe they'll go together at least, right? All right, so let's talk about a couple of things that might happen that changes things a little bit. Because you know by now it can never just be a straightforward, here's what you always do. Turning the sun back on. All right, so one thing that could happen. Notice, what did we do on these problems that told me what my limits were going to be? Where did they come from, my limits on my integral? Where did they come from in each of the problems we just did? Points of intersection, 11. There will be some problems where, let's see if I can come up with one. Something that'll work, that would be, wouldn't that be nice? Something that works? You want something? Yes, I do. Let's make it not too crazy, Jeff. Sure, okay, I'll let that's a little crazy. It doesn't matter, Jeff. It's a little crazy, too bad. I like it. And let's say I want to know the area between the curves from x So let me just do it the way that we want. Let's see, I don't know. It's gonna work nice. -2, so. So they would tell you, find the area between this and this on the interval -2 to 3. So my limits of integration are given to me. So let me ask you this. Well, let's do this. Let's try to graph this on that interval, right? What's the very first thing I should do?
Make them equal to each other?
Yes, I still want to know where they intersect, and you'll see why in a minute. Let's see, find the intersection points. Let's see what kind of problem Jeff has brought for us here. What's happening? So how do you do this? What's really nice is the x's die. Yes? Die. I could add 9 over. Or I could add the 1 over and factor. But one thing I need you to understand, if I factor a sum difference of cubes, don't you have a little dude, big dude? The big dude will always have complex answers. The big dude will always have complex answers.
By complex, you mean like imaginary?
Imaginary parts
Oh,
to it,
okay.
yeah. And I really want this to make sense. Why? So right now, if I just say this, x cubed equals, add 9 over, I get this, right? If I bring the 8 over, what does x cubed minus 8 look like? Doesn't it look like this? How many real intercepts can it possibly have? 1. Because x cubed minus 8 doesn't have any turning points. Right? It's always increasing, it has no turning points, it can have only 1 intercept. Doesn't that sound like an earlier homework problem? Maybe? Maybe, Jeff, we don't know, man. They all blur together. So I don't have to do that shit. I can just stick cube root and get the real answer. So what's the point of intersection? 2, 1. So if you put a 2 in, you get 1. If you put a 2 in here, just check yourself. 8 plus 2 is 10 minus 9 is 1. That's a nice way to check yourself. It's got to work in both, because it's supposed to be where they both agree. Okay, I like it. So let's try to graph this thing. So I have an interval to graph it on from -2 to 3. So let's see. X minus 1 is going to be easy to graph. Let's see this other dude. He's going to get a little crazy. -2 cubed is -8. Minus 2 is -10. Minus 9 is -19. And when I put a 3 in, I get 27 plus 3 is 30, minus 9 is 21. So I'm just trying to figure out what I want my y scale to be. Yes? So let's go up to like, maybe we go by, what do you want, Jeff? 4s. All right. And graph this dude in blue. Why not? Y equal x minus 1 is going to be nice and easy. So at -2, that's at -3. At 0, it's at -1. At 2, it's at 1. That's important. You made this horrible. At 2, it's at 1. And at 3, it's at 2. So there's that. And that's all I have to graph, because that's the interval they gave me to worry about. Yes? So what does x cubed plus x minus 9 look like? Well, at -2, we just figured this out earlier, and of course I forgot already. It's -19. So -19. And then let's do a few more. At 0, it's at -9. At 1, it's at 1 plus 1 is 2, and it's -7, it looks like. And at 3, well, let's see. At 2, it's at 1. We know it has to match up. That's the point of intersection, yes? And then, so all I'm doing is, you could even make a table of values if you want to. And then when you plug a 3 in, you get, well, what did I say, 21? So then here's what this guy looks like. There's your cubist shape. Oh yeah, it's not by arrow, so I just care about there. So what is the thing to worry about here? What did I say earlier about this area? Is it allowed to be negative, the total area? No. Is there a function on top throughout the entire interval?
The interval we're good.
Yeah, I want to know the integral from -2 to 3. I want to know the area between the two functions from -2 to 3, and the answer cannot come out negative. It's supposed to be a physical area. So I can't quite do this because there's a point where things change. Because I want this to be top minus bottom. Is there a top?
Yeah.
Phrasing. Okay. Is there a function on top from -2 to 3? No. Because at 2 they change, don't they? Okay, so if they don't give you an interval and they just say find the area bounded by these two functions, you just find the points of intersection, and that tells you what your interval is going to go from to. Those are kind of nicer. If they give you an interval, you still have to find the point of intersection because you might have to break the integral up. I can't do an integral from -2 to 3, but is there a definite function on top from -2 to 2? Yeah, the line is on top. So I can find this area by doing the line function minus the cube function plus, so that's this area, and now I can add this area in. But again, which function's on top now? And what do I go from to?
Or 2 to 3.
2 to 3. Let's see, yeah, x cubed plus x minus 9 minus x minus 1. So again, this is top, bottom, top, bottom. So why do we need 2 intervals here? We didn't before, because in each of the problems we did on that sheet, the same function was on top through the whole interval, right? How many times could the functions meet in your interval you're given? They could meet a lot. You could actually break this integral up into several. I mean, you could have something like, oh, shit, right? I mean, that's possible. I'm not telling you it's going to happen a lot.
Would, like in sine and cosine, would the areas between those things be symmetrical?
Could be,
Right?
unless they're off phase,
Yeah.
right? So it's a good idea. If they're not off phase, then probably you could figure out a shortcut. Possibly. Depends on a few things. Those intervals are not difficult, right? And do you see how this point is the point of intersection, correct? So the point of intersection could be where you have to break the intervals up. So let's see, we get interval -2 to 2. Let's see, x minus x disappears, so then I get -1 minus x cubed minus -9, which is plus 9. Is that cool? The x's cancel. -1 minus x cubed plus 9. And then, of course, you get plus integral 2 to 3. X cubed, the x's cancel, and then I get -9 plus 1. What did I do here? Jeff, here's this one. -1 plus 9 is 8. There you go.
Oh.
And then here you're going to get x cubed, the x's cancel, -9 minus -1, -9 plus 1 is -8. So what you're going to see is these are just going to be Oh, there's the negative one. Oh, it's fine. Jeff, you're awesome. These are going to end up being flipped, which makes sense because we end up having to flip which one's on top, which one's bottom. So that's 8 minus x cubed. X cubed minus 8. And then those are nice ones to integrate. And then I don't care anymore. Just plug this stuff in and get something. Yes? Okay. I sort of care. I don't care enough. While I'm thinking about this, did we talk about odd and even symmetry functions and how they interact with intervals? I can't remember. There's a brief mention in the book. It doesn't happen here. I don't get any help because is this function odd or even? It's got an odd power and an even power, so it's neither, right? So, is it pretty cool with that? I mean, there's more to it, but you just plug the shit in and get it. So real quick word about odd, even things, because it could help in some of these. Somebody remind me, what's an odd function look like? Officially, not just one that is weird. Okay, I like it. So the most basic one would be like x cubed, right? Or you could use sine. Let's use sine. It might be easier to think of in this context. So sine looks like this. So odd means it's symmetric through the origin. So if I pick a point, draw a line through the origin, its mirror point is over there. That's odd symmetry. So if I go, what point is that, by the way? What x value is this? Okay. So if I integrate from negative pi to pi, can you guys see what's going to happen? Whatever area this is the opposite of that, right? So this would be 0. So the integral from negative a to a of a function that's odd is 0. Right, so that's one nifty little thing. There's a problem in the book like x to the 4th sine x or whatever it was. And it's impossible to integrate that by hand, but you have to realize the function is a certain type of function. So what about even functions? What's a trig function that's even?
X squared.
Probably, no. A trig function that's even. Probably cosine. And again, the idea of even is the y-axis is the mirror, right? So cosine looks like the octopus, or whatever you like to call it. So if I, let's say I go, what's this? Good. Obviously this doesn't cancel, correct? But the integral from negative pi over 2 to pi over 2 of cosine is equal to, can't I just find this integral and do what to it?
Multiply by 2.
Multiply by 2. So you can see how they're related. This area is exactly the negative of that area, since I'm going symmetric. So that's going to cancel. This one, the area is the same. It's not the negative, so it just doubles. That is sometimes useful.
I have a question.
Yes?
Would there ever be a problem where you have to integrate, but like one of the points in the middle isn't defined, or does that change anything?
Oh,
Like,
okay.
for example,
That's I love it. That's the other thing I want to talk about. Thank you, Ricardo. There's a problem in the book. It's not exactly this, but it's kind of related to this. Let's say I wanted to do this here. You can find the antiderivative of this, correct? And then you can plug these values in, correct? And you get a number, but you would be completely wrong. Because there's one little thing about everything we've done with the function that's in here is it must be continuous on this interval. Is this continuous on this interval? Let me make this a little more interesting. Let me make it this. Well, that's really more interesting. It's the same thing basically, but the reason I did that is because if I look at this, does anyone know what x to the negative fourth looks like? What does 1 over x look like? X to the negative 1. You guys should know that one. Most basic hyperbola, right? Okay, it's hard to do. So when I raise it to an even power, it's just going to take this negative piece and put it up here. Because now it's got to be positive, so now it's easier to do. It's like an infinite volcano, right? Whoa, that's nice. So the lava can never get out. I'm coming for you. Oh shit. All right, so that's nice. We can live next to them. So it's going to look like this. So I'm trying to go from negative 1 to 4. This goes forever up. Isn't that a problem? There are some situations where the area actually comes out finite. It's not necessarily infinite, but the bigger issue for us is, does it match what we need in this class to be able to do it? No, it's not continuous on this interval. Okay, that's basically what you're asking for.
Yeah.
And real quick, do you guys understand how much this just keeps going forever up, right? So it seems like that area should be infinite, but some functions get so close to the axis so quickly that the area kind of doesn't grow fast enough to go to infinity. I don't know if you guys can you wrap your heads around that? No? Whatever, Jeff, you're weird. Okay. Let me give you a little, all right. If I add an infinite number of positive numbers, what would the answer be? You would think it'd be infinity, right? Not necessarily. Real quick, watch it. Is this positive?
Yeah.
All right. Is this positive?
Yeah. Yeah.
Why can't I do this forever? Forever and ever and frickin' ever. What will my answer be? Less than 1. What will my answer be specifically? Does anyone know? What's 0.3333 forever? 1/3,
yeah.
right? Which is 3/9, yes?
Yeah.
So 0.333 forever is 3/9. So 0.222 forever is 2/9. So 0.111 forever is 1/9. So there is an infinite amount of positive numbers that I added, and I didn't even get to 1. I didn't even get to 1/4. I didn't get. Anyway, sorry. So that does it kind of relates to this. It really depends on how quickly does that get close to that. So the areas, they're still there. They're still positive area, but they're getting so tiny so fast they don't go to infinity. Maybe I might have gone a little too far, but what's new? Okay. All right, so this comes up in a few places, this idea. Let me see. Oh, that's incredible. I love it. We got time. Let's try a problem out of the book. Because when I make them up, it gets really weird. Let's see. Boom, boom. So this is all section 6.1, if I didn't mention that earlier. All right, let's see what we get. Ooh, that's yummy looking. Let's see. Yeah, let's try that one. I don't know what's going to happen. Let's see. Good. I want to find that kind right there. Where's that at? Okay, I like it. Well, all right. All right. Let's see what you guys think. Okay. So what if I have 0 to 2 pi. I want to find the area between these two functions on this interval. I like it. So what do you want to do first? Or what do we have to do first? I should say like that. You might not want to. Huh?
Intersection.
It's intersection. Try to use 35. that's basically almost always the same thing. There will be a little bit of variation depending on the function, but normally you just set them equal to each other. Oh, red, you're dying too. All right. So I just set them equal to each other. All right, what's the next step? What do I always do? Get everything with an x in it on one side. Right? So add cosine. And then I can divide by 2. I love it. See? I mean, it's still an equation. It's got to operate by equation rules, right? And when is that true?
0.
0. And right. Okay. So is there a point of intersection in the middle of the interval they gave us? Somewhere? No. The interval they gave us is exactly where the things intersect. So it wasn't as interesting as I was hoping. But that's still okay. We still have to do this. Let's do this. Now I want to graph each of these. From 0 to 2 pi. I guess it would be better. So let me slow down here, jump over. 0 to 2 pi. So it's 0. Let's do, let's see. So I need more colors. This one in blue. So it's 0, that's going to be at
1.
1. Let's do this. And let's put 2 pi on there. Let's put pi on there. Let's put pi over 2 and pi over 2. Bam! All right. So pi over 2, it's pi over 2.
Oh, 0.
0.
Sorry, I think so.
That's all right. And then at pi, it's -1, right? I don't know where the point is from your perspective. And then at 3 pi over 2, it's at 0 because it's y-axis. Cosine doesn't like the y-axis. And then at 2 pi, it's back to 1. Now I know these guys agree here and here. Right? That's the work we did there. So I know it's going to start, let's just do you in black here. I know the other one's going to start there. When I put a pi over 2 in, cosine, of course, is 0. So 2 minus 0 is 2. Is that cool? When I put a pi in, what's cosine? So I need up higher. Maybe Jeff. Dom, you, Jeff. Not negative, Jeff. Yeah, so at pi, cosine is -1, so 2 minus -1 is 3. Is that cool? Right, at pi, cosine is -1.
Oh, yeah.
2 minus -1 is 3. At 3 pi over 2, cosine 0, so I get 2 again. And then at 2 pi, cosine is 1, so 2 minus 1 is 1. So they meet what it's supposed to. So here's this guy. Not surprisingly, that's a cosine that's been flipped because that's what that part says. And then I get this guy. Is there anything coming to mind when you look at that? You know, I think of Rolling Stones, or I think of Rocky Horror Picture Show. So I want to find that area. There's a very obvious function, bigger function. Like, how do I set up this integral? What's it going to be from to? From 0 to 2 pi, because I know it's going to be dx, because my functions are functions of x, so then I look at what my x is doing. I like it. Now let me ask you this. If I had to do dy, what would my limits be?
-1 to 3.
Yeah, -1 to 3, because then you look at what your y's are doing. That's that, right? That's it. So the biggest thing in most of chapter 6 is, will it be integral dx, or will it be integral dy? That sets up like a lot of things. What function's on top?
2 minus cosine.
2 minus cosine. Minus cosine. So we said from 0 to 2 pi. We kind of gave it away, of course, earlier, but hold on. All right, now I almost don't care. We should be at the point where this is the simple shift. So I get 2 minus 2 cosine x. What's that interval? Yeah, another interval.
2x.
2x. Yeah, let's do this. So minus 2, what's the antiderivative of cosine? Sine, right? Okay. So no negative there, right? From 0 to 2 pi. So I get 4 pi minus 2 times sine of 2 pi is, sine of 2 pi is 0. And when I plug 0 in, 0, 0, so I get 4. That's neato. So the area of this open mouth is 4 pi. It's kind of like prettier than we might think was going to happen. Maybe. And you guys look stunned. But really, I think the hardest part of what we talked about today was if it's dy, because we are not used to thinking like that. Right? I think that should be the hardest part, because seeing, if you just give yourself a rough sketch, it doesn't have to be beautiful, it doesn't have to be perfect. You just need to know what's on top and what's on the bottom, just so you can put things in the right place, right? But it's the dy stuff that'll be really freaky. Okay, yeah, that's plenty. I'll let you guys out of here. So next week we'll get into some really nifty stuff. Yeah. I'm sorry. I hate that phrase now brings terror to people. That's next week will be where I need to find my visual aid, my physical visual aid. Yeah, we'll see if I can find that, hopefully. All right, guys, let me know if you have any questions. Otherwise, I'll see you Monday. Have a good weekend.